that class. I do know, I've taught it long ago. And usually the way most undergraduate courses are broken down, the final is the heaviest weight. For up to, I have it sometimes 40–45%, but then you get midterm exams and quizzes or homework usually. So the final isn't, it usually isn't the majority of the class grade. It's usually it's a larger percentage, but it's not the majority. But I don't know if there's some policy that it's supposed to be 50%. I'm not aware of it. Because I frankly, like in my classes, I have a standard set of guidelines that do, and I just follow the guidelines. Most people do, but if they said it's supposed to be 50%, then
well, it's supposed to be 35, but the tornado made us not able to take the test, and then he just.
okay. You're saying it's supposed to be 35?
It was supposed to be, but he just.
Oh, in his syllabus.
Mm-hmm.
The syllabus had to get.
And then they changed it because.
What I would do, just suggest, is politely, not demanding, go to the instructor and tell him that you have concerns for the change in policy that happened. But don't do it in an arrogant way. You're never going to get anywhere with arrogance.
Yeah.
Remember, and instructors, a lot of times these guys don't know what to do either, or girls, and they're just trying to do their best. Nobody's out there. Very few people are out to get you. I've had students accuse me of everything. I think I'm trying to destroy their lives. No intention. All right, before I get into what I want to change today, do you have questions about homework? I didn't teach you that, I think, this summer. Yeah.
5.7, it's in air, stationary conductive loop is positioned next to an infinite extent line of current.
All right, hold on, let me get this drawn. So we have a current I, and then we have, is it a square loop or?
It's a square loop, centered on the y-axis.
Centered on what?
On the y-axis.
Oh. Wait a second. Let me draw this thing up. So this is X, Y, and Z, right? Now, go ahead and tell me where this, the
So-
current's on the Z axis, isn't it?
Yes.
Okay.
And the conductive loop, the bottom part of it is on the y-axis. And it's just a
How
square.
far, so it's like this, right?
Yes.
Okay, go ahead with the dimensions.
It's a distance 4 centimeters away from the line of current.
So A is 4 centimeters. Go ahead.
And the line of current increases with time.
All right, they give dimensions to the loop or not?
Yes, the it's 2A is the far side is 2A.
So the
it's
width
8.
here would be A,
This is A.
okay? And the height,
I think they
A.
go the height.
square? It's a
Oh,
square?
yes.
Okay, go ahead.
The line of current increases with time. I of t is equal to 110 t.
So I of t is equal to 100 and, oh, this is a classic problem. 110 t amps, go ahead.
That's amps per second.
Wait, this is not I of t, this is the rate of increase?
Yes.
Oh, so they're saying di dt is equal to 110 amps per second?
Yes.
Okay, go ahead. And that means I of t is just equal to 110 t, right? If di dt is a constant, which is 110, integrate both sides, you get I of t equals 110 t plus some constant. I'm assuming that constant's 0 for now. It won't matter if it isn't. Go ahead.
And they're looking for voltage loop.
All right, and I assume they position some break here, and they'll have plus or minus VEMF, like that? Is that right?
Yes.
Take a look. Okay, this is the classic problem. I went over basically this problem last time. I don't want to do it again. I want to make sure everybody understands this. So, anytime you're doing a problem like this, this is induced EMF, one term. We know that VEMF that would be induced induced is equal to, it's really the integral of E dot dl in the counterclockwise direction, and it's equal to minus d dt of the integral of B dot ds over the surface. Now, a lot of this I'm just restating, and these are sort of abstract concepts until they're applied to the problem. Everybody with me on this? Now, come down here, that EMF measured would be plus on top, minus on bottom, and the actual induced voltage or induced electric field would cause current to go in that direction based on that set of equations. So now, the next part we have to do is this. We have to first find, and this is where it gets a little tricky, so I want you to focus on this one. If I have I going up, y'all with me on this? Then the magnetic field would be in the azimuthal direction. It would be in a direction like this. Do y'all follow me on this? And right here in the plane where x equals 0, in this plane that I'm showing you, the magnetic field would be into the border in the minus AX direction if we're going to use AX, AY, and AZ. Follow me, class? Y'all see that? Use your right hand, put it in the direction of current. You can see that the actual B field or H field is into the board. Y'all follow me on that? All right, now the value of the B field, or you can get H if you want, but I'll just get B. B of T would be equal to mu, right, mu naught in this case, times I of T over 2 pi, and instead of rho, I'll use just Y. And it would be in the minus AX direction. Take a good look at that. Y'all agree with me first? You know, the H field would be I over 2 pi rho, right, in the A phi direction. In this case, A phi becomes minus AX at that plane, right? Can you all follow me on this? Now, I put the mu there because it's the B field we want, right? So the next thing I'm going to do is get the integral of B dot ds. This is the important part. Please listen to me. So when I get, and I'll just use the simple magnetic flux right here, I have to get the integral of B dot ds. We have B, so I just put down mu 0 times I of t over 2 pi y in the minus AX direction. Now I have to dot that with ds, and here's where it's important you pay attention to this. I'll give you a second to catch up. That's the differential surface, ds. It has a magnitude and it has a direction. Y'all follow me on this? Y'all with me? I'm talking about the ds that would be inside that loop. This is real important. It's magnitude and direction. The magnitude would just be dy dz. Do you all see that? With me? Differential would be dy this way, dz vertical, correct? So I'll put that here. Now, what is the vector direction of that surface? Do you remember how I told you to get it? You got it right here. I hope you all do. Anyway, take your right hand, and the only thing you have to do is grab the grab that little square there. Your thumb points in the direction, all right, of the differential surface. Viewed from this side. Y'all with me on this, class? It's positive what? AX, correct? Y'all see that? Positive AX? So this is now going to be positive AX. Now we have to put the limits on this, and I want to do this being a little more formal than I usually am on this problem, but when I get dy, that goes from A to 2A, doesn't it? Y'all see it starts here, goes to this distance, which happens to be 2A. So it goes from A to 2A. And Z just goes from what? Might as well make it 0 to A, right? It goes from anywhere to anywhere plus A, so I always I have a choice, make the anywhere 0. Everybody follow me on this, class? Remember this differential surface right here is the kicker on this one. Now, one thing you notice is I have AX dot AX, right? Which is 1, correct everybody? But there was a minus sign, so that comes out in front, doesn't it? Correct, class? Y'all with me on that?
Yeah.
I'm just bringing it out in front. Now do the integration, what do you get? The magnetic flux would be minus, and then mu 0 I of t, I'm just gonna leave it as I of t here, over 2 pi. When I integrate dy, I get natural log of y, correct? Everybody? So I'd get natural log of 2a over a, right? Or really what? Just 2. Correct, class? And what about the dz integral? Just h, right? Or the height a, right? Or a. So I'll put an a here. And that would be the that would be the magnetic flux right here that penetrates that loop. Follow me? Now remember, I'm viewing it from this side, so the VEMF is in this direction. Y'all follow me? It's a counterclockwise induced volt, but the voltage that would be induced by an electric field, such as the impressed electric field, would be in the counterclockwise direction. Some of this is a little hard to appreciate right off the bat. So that is the actual formula for this. Now I have to take the time derivative of it with a minus sign in front of it, correct? So I'm going to go ahead and just expand this a little. I'm going to say this is minus d dt of this flux. So it's minus mu 0 over 2 pi times I of t times a times the natural log of 2. And I hope you appreciate the fact I'm trying to just take that and stick it in the equation so you see every step, everything that can happen. Now the obvious thing is the negative signs cancel, don't they? Minus 1 times minus 1 is 1. So I'm going to get rid of those. And now you see that time derivative only operates on I of t. Everything else is a constant. That would be the mutual inductance button. So now I have mu 0 over 2 pi times a times natural log of 2 times di dt. And di dt in this case would be 110, right? That was stated at the beginning of the problem. Correct, class? So it's just times 110. And that would be the induced voltage measured plus to negative here. And we can put the values in. If you got a calculator, you can help me out here. So that means the VEMF would be equal to mu 0 is 4 pi times 10 to the minus 7 divided by 2 pi is 2 times 10 to the minus 7. And then A is what again? 4 centimeters? Is that right?
Yep.
So it's 4 times 10 to the minus 2 times natural log of 2 times 110. And that should be the voltage. If anybody can give that to me, you can tell me if it's right or wrong. 600 nanovolts? 610 nanovolts? Is that what you guys got? Is that what the problem's answer is?
It's negative.
Well, wait a second. Does he have it plus the minus? I better look.
He's got it in the negative.
It's,
His differential service is
you're
in the
talking
negative there.
for clockwise direction for
Hold on for a second. Let me just get to it. Oh. Yeah, he's got the voltage over here. All right, so if you take a look at this, this is plus to minus. Just move it around here. It's really the negative of the voltage I show you. Do you all see that, class? He has it. He wants the plus here, negative here. Just shove it around the loop over here. And you can see that the negative and positive are interchanged in his. He puts it on the far side, probably just to confuse you a little. But whenever you're doing a problem like this, here's a tip. Regardless if there's a resistor there or not, break a small little gap and find the voltage across that gap based on the method I showed you, where you then include the resistor. Now here's something I want to show you. See how that's a positive voltage right there? I want you to follow me on this. That means in this loop, when it's broken, you develop a plus to minus voltage, VEMF here. Now just listen to me. Current is being forced around in that direction. Do y'all see that, class? If you would just say this loop is closed, current would be forced around in this direction, And the only thing that would limit that current is the internal resistance of the wire. You all follow me? Now, if I put a resistor anywhere here, the current that would move in this direction, in that direction, would be equal to the VEMF divided by the resistance, period. You all follow me? So that's the key with these things, because what people do, they find ways to turn this problem, they'll find the current in the wrong direction is really what I'm going to tell you. They do this all the time, but if you see the way the actual, the way the induced EMF is causing charge to circulate, that's the way the current will flow. And the current will flow based on VEMF divided by the value of the resistance, because that VEMF technically, if the loop was a closed loop, it would be uniformly distributed around the entire loop. All right, it would be a differential electric field around it. Okay, another problem. Must have got that test back today. Is that what happened?
No, it got canceled in the middle of the storm, so we didn't get to finish it.
And he's not giving it.
Today?
No, yesterday during the storm, we were taking it 15 minutes in, it stopped, and then now,
On Tuesday.
yeah, Tuesday, yeah.
And he's not giving it.
So he said he's gonna grade our best attempted problem, make that 5% of our final grade, took the other 15 from the 20% and added that to the final.
If you can come up with a better scheme, go collectively to them in a very calm, reasonable manner. You might be surprised what happens.
Yeah.
But I mean, that's, I don't know, I was at the rec center yesterday. This thing went off recently. So I really don't care about these things. But they made us all go down into a fallout shelter area. I couldn't believe it. We were there for 45 minutes. I said, come on, man. Things are all this solar. So what happened in this building? The alarms go off?
Yeah.
This is a solid brick building. That's not what's gonna happen here. Okay. So today, I mean, is there any other questions about induced EMF? I mean, it's what? This is transformer action, basically, is it, class? Anything at all about that? Because I'll tell you, that particular, what I'm showing you here, I'm gonna give you some more problems that are a little more difficult tonight to deal with this concept being applied. People get confused on this stuff all the time. They make mistakes, some mistakes. So in Whitmer's book, he breaks down the induced voltage into two types. One, he says, is motional EMF, and the other is due to the time-varying magnetic field. And we'll talk about transformer action in a second. So now I'm going to talk about motional EMF and what that means. And this is the principle a railgun operates on, in a sense. So if you have just a current I, matter of fact, before I come there, let me explain one thing. If you have a magnetic field that's uniform, doesn't vary spatially, and I'm just going to call it B, and I'll say it's into the board, and B is the same everywhere, does not vary anywhere. Just B, and call it B0, it's a static field. Then if you have something that is a conductor, this is the key, it has to be a conductor, not a dielectric. A dielectric or conducting rod, anything like that. And it's moving through this field. So I'm going to just draw a bar here. And the bar is going to have a length L. And it's going to be moving with a velocity V. Now I hope you, and this is a conducting bar, you can appreciate what's going on. There is an induced EMF on this. And this is important to understand. So what's going to happen is there's going to be an induced electric field that they call EI, or an impressed electric field. That impressed electric field is actually equal to V, the velocity crossed into the B field. Now I'll tell you where that comes from. Normally if they say they have a charge, Q, moving at velocity V, then the Lorentz force on this, if there's a B field in it, is QV cross B is actually equal to the actual magnetic force. Do you remember this when we did the magnetic bottle? V cross B? How many do? All right, well, what they actually do is this. They're saying this is the same force, same type of electrical force that acts on charges as an electrostatic force. If you have a charge that's static, there's an electric field, it's the same type of force. So what they do is divide this by Q, and they get an electric force that's due to motion through the magnetic field. They can just term it EI. It's an electric field in a sense, same unit, same everything, but this one's due to motion, not due to charge, just static charge. You all with me on this, class? So you have to have motion for this to occur. So that would be the impressed electric field right here. Now follow my train of thought. You all get that, class? You got something moving through a constant B field at a given velocity. The induced electric field, think of it that way, the induced field is V cross B. Now look at this, the B field's going into the board, right? If I get V in that direction crossed into B, you see how the electric field is in this direction, vertical? How many see that? V cross B would be straight up, right? So there's an impressed electric field in this direction. Now that electric field causes charge to move. And it will cause positive charge to accumulate here, and negative charge, if you will, or a deficit of charge to happen at the other end. You all with me? Now if you went there and you had a meter and you measured the voltage, if you somehow could do this, and you put your positive lead here and your negative lead here, and you looked at your meter output, then this would read a VEMF equal to simply EI, the impressed electric field, times the length of the bar, and it would be positive. I'm keeping this simple. Do you all appreciate that? So V cross B is an impressed electric field. Technically, you're supposed to integrate that over the length of the bar to find the voltage difference. But it would be plus on top, negative on the bottom. Do you all follow me? Now this is a type of a generator. So if this bar was moving through space at velocity V and B was into the board, there would be a plus to minus voltage right here of VEMF, if this is a conducting bar. And if you actually found a way to connect the resistor here, then current would flow through that resistor in this direction, and that current would simply be VEMF over resistance. Do y'all follow? So it's almost like a generator in a sense. Actually, it is a DC generator. You've had the difference between DC and AC generators, huh? Anyway, that is a DC generator. It's monopolar, never changed polarity, never changed magnitude. Problem is, things kind of move forever in that same line. Just ain't gonna work that way. So where does something like this actually become of interest to everybody? Well, you might say right now in space we have tons of satellites that are orbiting, right? The Earth has a weak but nevertheless apparent magnetic field. And the Earth's magnetic field, don't write this down, just listen here. This is the Earth itself. Then the magnetic field of the Earth, the lines look like this approximately. And at the poles, they're just about vertical. They're pretty vertical right here where we are. Only around the regions of the equator do you get any kind of real horizontal component of the B field. Do y'all follow me? When you talk about orbiting satellites, usually satellites are either geosynchronous or low Earth, but they're in the presence of that magnetic field. So when a satellite's moving through a weak, but nevertheless apparent magnetic field at a very high velocity, it generates an induced electric field that generates a voltage across its body and separates charge. You all follow me on this? Now that charge is there, and it's got to do something. And it'll find a way back to the actual negative. The positive and the negative charge will get back together, and they'll do it through the plasma of space. You all know in space there is a very small amount of ionized particles or gas. You all with me on, unless you're talking about very deep space. But so what happens is you get these arcings, and this is a true story. I remember learning about this at NASA. So long ago we had a satellite called Telstar. Has anybody ever heard of that? The first communication satellite. Do you remember what happened to it? It crashed in Australia. Now here's the deal. They went and they figured out all the physics involved with orbital physics. They figured out the collision cross-section of the plasma, the rate that this thing would actually, its orbit would decay by losing energy. And they knew it would be up there a very long time. But the thing was coming down at a much faster rate. Where did we go wrong? And somebody figured it out. It was basically being a monopolar DC generator, and there was an arcing through the plasma occurring. So this thing's moving, it generates a voltage because of the velocity. That voltage is then shorting out through the plasma, causing I squared R losses. You all know you don't get anything for nothing. So what's really happening is that thing is, most of the energy that's being lost is actually heating the plasma space, not from the collisions that are occurring with the actual plasma up there. And so the dominant thing that brought the satellite down was the heating of the plasma. It's the first time they actually start thinking about that. Now if you do any kind of orbital physics with anything like that, they always work out the induced voltage and the possible power loss into the plasma of space. Y'all follow me on that, class? The thing crashed, and by the way, the crazy thing was that until that thing started decaying, it never occurred to them, even though some of these guys were plasma physicists, that could be a major problem. They never did look at it, which I thought was strange. And then in the history of really our conquest of space, there's been unbelievable mistakes. We've lost things on Mars because of unit conversion problems, billions of dollars. I'm not kidding about this either. It's like, I don't know who came up with how to do a fail-safe checklist, but they really blew these things in a way that it boggles my mind that it can happen. Do you remember the Challenger blowing up because of an O-ring? Anybody? You know what I'm talking about? The O-ring wasn't tested at liquid nitrogen temperatures. It was going to be used with liquid oxygen. How can you guys miss these things? It was just one of those things that happens. Anyway, lesson to be learned about this. That is a dominant effect with any type of orbital mechanics, so remember that. Now, in his book, here's a classic problem that is based on this principle. So, if I have two rails, perfect conducting rails, assume they're infinitely long. And these are just infinitely long. And they're separated by a distance d, and they're parallel to one another. Then I have a resistor here, and I put a bar that's going to be in contact with those rails. And this bar is going to be moving at a velocity v down the barrel, you might say. And if there's a B field, it's uniform everywhere. It doesn't have to be uniform, but we're going to go ahead and do that. Y'all follow me on this? It's moving this way. I want to find out what the current is that flows here as a function of time. Now you all see what's going on, right? We could do this problem two ways. We could write an equation for the amount of flux that penetrates that closed surface as a function of time. Remember that bar's moving. Then we could take the time derivative of that flux and put a minus sign, and we would get the induced VEMF. That's one way. The simpler way, if the B field's a constant, is just finding the impressed electric field here, which would be V cross B. Are you all with me on that? I give you a V, I give you a B field, just take V cross B. You can see it's along the axis, right? Everybody with me on that? If that's EI, that means the voltage that would be developed between here and here, this being the positive side, and this being the negative, this VEMF, would be equal to simply that EI times the distance D, or really it would be V cross B magnitude times D. That's VEMF. And then if you divide it by R, that would be the current. Y'all with me? I'm going to make a point here. Y'all with me on this? Okay, that would be the current that flowed. Do y'all follow me on this? Now, how much power is actually being dissipated by this resistor? What is power? Isn't it I of T squared times R? Right? Or, in this case, it's what? It's this squared over R. So it's going to be V crossed B magnitude times D. Got to square that thing divided by R. The resistance. That would be the amount of power in watts dissipated. Now, we could go through this if we had a little more time. You don't get something for nothing, right? All right, if this thing's moving through there and generating that much power, that means there has to be a force resisting that motion. Y'all follow me? Has to be. As a matter of fact, that force right there, if you think about it, you know that, work is really force integrated over distance, right? But if you think about how you would get power, what is it? You can do it this way. I know whatever the force is on this bar, right? There's a force on this bar. And I know the integral of that force, actually let me do it this way. Force dot dl is the differential amount of work done, or energy that's going to be used up. If I take a look at that, and I take the time derivative, so force times dl dt is equal to dw e dt, that is power. Remember, the rate of change of energy is power. Are you with me? And what this is saying is force times velocity is really power. So I've got the power, over here I have the power. And please forgive me if I'm not exact with some of this stuff in terms of the notation. Would be equal to magnitude of V cross B, square that, or times D squared, times D and then square it, over R. Y'all see, I just equated the force times velocity that's pushing that thing, something has to be pushing, equal to the actual, what? Power being used by that resistor. Now take a look at this. Y'all see how this is gonna have a V squared in it, and this has just got a V? But when you do this, you find out that the force itself in magnitude will be equal to simply V proportional to B squared proportional to D squared inversely proportional to R. And that's how you can get the resistive force that would be on this if you were physically pushing that with some other external force. It's a basic physics principle. Now, something else that I can tell you about. This is being used as a generator, right? It's causing current to flow, causing a voltage to be developed. By the same token, if you had this situation where you had rails like that, and now I'm going to put a generator, V of T here, a voltage generator, and I have a bar here, separated by distance D, and I have a B field everywhere into the board. Just showing you something right here. It's really, that was actually a generator. This is going to be a motor in a sense. It's going to move things. All right, now follow me on this. I've got a B field here somehow. I don't care about how it's there. Now, when I put that voltage on here, it's going to cause a current to flow in this direction. There has to be something that limits that current. For now, just assume it flows. You all with me? Now, what do you know about force? The differential force on a piece of, if you have an IDL and you have a B field present, that there's a differential force that's equal to IDL crossed into B. Correct, class? With me? IDL cross B. Now look at this. IDL, right here, coming down, crossed into B. You all see how the force is this way? Just do it with your finger. If current is flowing this way, don't worry about the amount of current right now. You got IDL crossed into B, right? Force going that way. That's the principle of a railgun. What you do is you have basically some thin foil that conducts from the top to the bottom rail, and when a lot of current comes through, it becomes a plasma. Well, that has got a B field inside that barrel caused by these current elements here, and it shoves that thing down the barrel. And the amount of force is proportional right here. It will be proportional to I squared. Now, I'm actually, it's proportional to I. But I want to tell you one other thing about a railgun, just so at least you have some common sense about it. With a railgun, you have two very long rails, like such. And you've got current flowing this way. Then there's the actual projectile that's going to be moving out. It has something called the armature where the plasma is, and the current flows this way in the back part. You all with me? Now just think for a second, if you've got infinitely long current conductors for a second, you know the B field would be going into the board from the top one, right? From that one coming back, it would also be going into the board. You all see that? The rails themselves, as the current flows, create the magnetic field that's going to force this thing down the line. That's how a railgun works. And I don't care about the exact physics. You have to appreciate what's going on. Now, what you have to understand is, because this is connected between the top and bottom rails by something that turns into a plasma, whenever you have plasma touching any piece of metal, it ablates the surface, it damages the surface. So the problem with any railgun is surface ablation, and the higher the temperature that plasma is, the more problems you have, the faster it ablates. So I learned this lesson doing this. After every shot, basically you have to clean that barrel and you have to smooth out the rough spots if you're shooting at any appreciable velocity at all. And the new, I don't know how they get around this, they have come up with all sorts of clever ways of preventing that. But the upper limit on the velocity, because those rails are ablating, is about 6 kilometers a second. That's the peak value. Now, can anybody think of it, why somebody would want to shoot something at some ridiculously fast rate? There's one thing that's overriding all others in terms of an industry need. Well, partially true. They want to get satellites up there without spending a fortune on a rocket fuel. 90% of the weight of any object you get into orbit is really in the fuel itself. Do you know this? So they want to get something where they basically want something to shoot it into orbit. It takes 25,000 miles an hour without the atmospheric losses to get something out of the Earth's gravitational pull if you want to go deep space. But they're trying to do it where they get a railgun to fire the thing. Then some sort of boosters or something take place so they save fuel. Now that is a big, big deal. Has anybody else heard about this at all? You all know that launching things into space nowadays is, everybody's doing it because of satellites, right? And the biggest problem is cost getting the thing up there. And that's how come railguns become an interesting thing. And people, I don't even know how many different groups are working on this, but it is something that they're spending a fortune on. The military has railguns, but they're used as weapons. And I think the next Aegis class cruiser or destroyer is going to have the 5-inch gun replaced with a railgun. I haven't been officially told that, but unofficially. All right, next thing we cover, I hope you didn't mind that. I'm just trying to keep you informed about stuff. And I could ask you questions about that related to that. I'll, of course, would provide some that were similar. So now, the next thing we have to do is talk about magnetic lifting force. This is the prior chapter. Now, you've had this in physics, right? So the classic problem they do is this. They take a bar, and they assume it's a bar of iron, and then they put a little gap down here, and they say the cross-section of this bar is A, here. And they're going to have the length of this be like L1, the mean length, and they'll have the length of this be L2, and there's going to be some gap dimension, and call it just L gap here. Then they'll put some coils of wire. They'll have N turns, and they'll put a current I here. And they'll want to know what the force is that's pulling this thing up. That's the magnetic force. That's the question they want. So, what's usually done in the book is first they close the gap and they find the amount of magnetic flux that flows through there. Y'all follow me on that? We can do this, but I'm just telling you what usually happens. Usually what they do is this. They're going to say that I'm going to have a certain equivalent electric or a magnetic generator. I'm going to have plus to minus Ni. That would be the magnetomotive force. Then I'll have a reluctance here that will be equal to L1 over mu divided by A, and that would be associated with this upper part. And they'll have a second reluctance down here. It will be L2, and let's say that that's A2, but it's really not a problem. L2 over mu A2, and we can assume mu is much, much greater than mu naught, so it's a magnetic material. And then the first thing they do is they say if there is no gap, they want the magnetic flux that's going to flow. They say magnetic flux with no gap would be equal to Ni over, I'll call that 1 R2. And then when you add the gap there, the circuit simply changes like this. Still R1, still reluctance 2. And then you're going to have the reluctance of the gap. And because there's two gaps, it will be 2 times L gap over mu naught A, because it's assuming an air gap. So it's twice the actual reluctance of one of those gaps. Do y'all follow me on this stuff? So I'm trying to make this as easy to understand as possible. Now, if you look at this right here, if I have the magnetic flux here, I can get the B field, right? I can say the B field would be equal to the magnetic flux density over the cross-sectional area, and assume all the areas are the same. A1 is equal to A2. Then if I have that, I can get the H field, and the H field would simply be equal to the B field itself divided by mu. And then, y'all give me that right there. Then what they'll do is say that in these gaps, when there's a gap occurs, there's going to be a certain amount of energy density. Now I'm going to get to the chase on this one. I'm just saying that they will set up these circuits like so. They'll get the magnetic flux here from the actual flux here, and then if you want, you can get the total energy in the circuit. You can say that the inductance is really the number of turns right there times the flux linking each turn. So this would be L with no gap, or call it L0 here, and that would be, if you look at this, it's N squared. Or, instead of inductance, let me get the flux linkage. No, I'll get inductance. Never mind, I'll get inductance. And then they get the total magnetic energy. They'll do the same thing over here. Call this 0. Now for this one, the actual inductance changes, N squared over reluctance 1 plus reluctance 2 plus reluctance gap times 2. Y'all know what I'm doing here, how I'm getting this part? I'm trying to just show you this is one, it's called the macroscopic approach. This would be the energy in the system with a gap, and this would be energy in system without a gap. Y'all follow? Now, I didn't put the gap length or anything in there, but what will happen is when you take total energy of a system, or total magnetic energy, that's really equal to F, well, let me do it this way. The change in the total energy, magnetic energy of a system with respect to distance, and this can be dx if the gap itself here is assumed in the x direction. It's minus that is equal to the magnetic force. You remember in physics that you knew that the rate of change of energy with respect to, well, energy was equal to, or really work was the integral of F dot dl, right? Therefore, F dot dl was the differential amount of work. And if you take that, the differential amount of work divided by dx, length, that is the force that would be acting on that. I'm trying to just make an analogy to something that happened. Well, here I've got the energy in the first state. Here I have the energy, I'm sorry, this is the energy in the first state. If I take that and subtract it from the energy in the second state, the difference in that energy would be equal to the force. Or the difference in the energy divided by D would be actually equal to the force. I'm going about this in a way that's a little different from the book. the way Wentworth does this in a book, and I'm just gonna cut to the chase on here, he says that the areas inside the gap right here, where I'm showing you, and this is in his book, these have a certain amount of magnetic energy. Magnetic energy itself would be 1/2 the integral of mu times h squared over the volume. Now just appreciate that's energy density, and it would be integrated over that region. Do y'all follow me? Now the gap itself here is going to have just air, so it'd be mu 0. Mu 0, and then it's the integral of magnitude of h squared over the volume. What he'll say is the h itself is about a constant anywhere between the gap. So this will be 1/2 mu 0 times h in the gap squared. And the volume he's going to say is area times the differential distance right here. Instead of L, he'll have a differential distance. And he'll just call it D. And that's for one of them because there's gaps here and here. There'll be 2 of them right here. So this is the actual magnetic energy in both gaps. Now, I'm going to try it. This is the part, only thing you have to know right here. So this is energy in both gaps. And Wentworth knows that minus the rate of change, the magnetic energy with respect to distance or with respect to D is actually equal to the force. In this case, it would be mu 0 times magnitude of hg squared times the area. And that is the force that lifts the bar. So that would be this lifting force. In his book, he shows something, but I want to just tell you one thing you have to understand about this. This is the key. That's the lifting force if you have gaps on either side of that, all right? This is for a magnet like the one I've drawn, and now I'll be exact about this. I'm over. Gosh. Well, here's the deal. When you have a system like this, and you have a gap, like such, draw the equivalent magnetic circuit. After you do that, after you draw the equivalent magnetic circuit, you calculate the B field in that gap. Y'all with me? That's by taking the flux divided by the area, and then find the H field. You hear me on that? Once you have the H field, you go right to this equation. Take that value, square it, times the cross-sectional area, right here and here, right? There's 2 areas, cross-sectional area, and multiply that, or sorry, right here, by the area, and multiply it by mu 0, and you will have the force, lifting force. It's a very simple thing at the end of the day. I would start going through here, and I realized it was going to take a little more time than I wanted to get into. I'm already 5 minutes over, so I'm going to give you problems, and on Friday, the quiz that you get will be directly related to the problems of the last 2 homeworks. All right? So prior homework was, and like today's homework and the homework I get today. Okay, this is due Friday.